You can see my share screen, right?
Yes, I can.
Sir.
All right, awesome. So I guess this will be just me restating perhaps what I had in the initial proposal statement, but maybe it will make more sense as well now. So in the paper right now, we were looking at, hey, how do we simulate correlations that we get after performing some measurements on a entangled state, right?
Yes.
Now, so we can make that problem a bit more generic rather than making it specific to quantum, where we say, hey, if you're thinking just about playing the CHSH game, then the CHSH game is nicely characterized by this conditional probability distribution vector, P of A, B given X, Y, right? Where X, Y, A, B are both bits, and X, Y are the inputs, and A, B are the outputs. And so, for example, one probability distribution vector that, actually gets us the optimal value for the CHSH inequality looks like this. I'm writing it as a matrix. I'll quickly explain how to think of it as a vector. Let's think of this as P00 given 00, 01 given 00, 10, 11, and then P00 given 01, 101 given 01, and so forth. And now imagine we have kind of taken each of the first 4 entries and made them into a row vector over here, right? So let's say this corresponds to these 4 entries. These 4 correspond to these 4 entries. These 4 correspond to these 4 entries. And the final 4 will correspond to these 4 entries. Does that make sense? So you've got kind of a 16-dimensional vector, which has 4 probability vectors inside it. And you can think of it as either a 16-dimensional vector or write it as a 4x4 matrix. So, and the game that we are kind of thinking of that we are playing using, that we played in the quantum case also is just this, that Alice and Bob are just playing this game where they get X and Y as inputs and produce A and B as outputs. Is that okay? Any questions about this setup? I think you've reviewed it in the thesis as well. And
Yes, I remember. There is no problem.
Right.
Yes, sir.
So, so the problem, the one formulation that we could have is trying to set it up as an ML task is if I give as input this P of A, B given X, Y, I will allow as output the communication cost for simulating PAB given XY. Right, so we have seen one explicit protocol which provides us this simulation when, so the protocol is when the PAB given XY is generated using a quantum source. There's no, we don't necessarily have a guarantee that, we'll all, that the P should come from a quantum source. We could take this arbitrary mathematical object and then just say, hey, what's the communication cost for simulating it? Now, one way to think about it is an ML protocol might be that we have a neural network that has been trained And this is just potentially one approach. There might be others. And it has been trained on the optimal strategies for simulating specific P of AB given XY. Now, what do I mean here in terms of training? Or we could imagine that the weights, the parameters that we are kind of fine-tuning in the neural network are of the following form. We know that any PAB given XY can be decomposed into a convex combination.
Sir?
Yeah.
Sir, can you explain what exactly I should imagine when you say the word neural network?
Oh, okay. So that I can provide background reading. Yeah. So that's just one kind of class of algorithms that are known in or that are used in machine learning algorithms. Here, the idea is kind of, are you familiar with the perceptron? Think of it
Sorry,
as
sir?
kind of a. All right, so so it seems like you're not. So I'll share with you some reading material about neural networks. It's basically just an algorithm that basically will. It's a class of algorithms rather than an algorithm that you use in machine learning to learn how to classify things. Right, so it could be something as simple as, hey, you give an image as input, and the network has learned how to classify whether or not the image is of a cat or not. And so the output in that case would be just yes, no, given that you provided as input an image, and the network then says, hey, yes, this is an image of a cat. No, this is not an image of a cat.
Okay, sir.
So,
okay.
Right, how it works is basically it learns to figure out what are kind of important parts of an image. In this case, that would correspond to a cat image versus not a cat image, and then weigh that accordingly for whatever image you provide as input. So the training process will be a process in which it figures out, hey, what kind of weightage should I give to each individual kind of pixel, let's say, regarding, hey, what color it should have if this was a cat, or some group of pixels rather than one pixel, and then figures out, well, the new image that you've provided, what does it correspond to? So any P of,
makes sense.
but think of it, right? So we need not work with the neural network algorithm. We might work with some other one as well. The initial task is to figure out how to first model this as a learning problem. And there are some papers specifically for this as well, which I'll share. That's how could we model? Like, there are some people who have looked at this. I'm not satisfied with the way they used it, so I'm happy if people have kind of other approaches to suggest as well. So here, the way I'm thinking about this over here is basically, so this P of AB given XY can be written as sum over some probability weightage Q sub I, and then D of AB given XY, where this D are deterministic strategies, which are fixed. These are already known in advance.
Yeah.
We can actually enumerate them. What we want to know is, want to optimize over these probabilities Q sub I. Right, so at the end of the day, if you imagine that, you've got the space of all possible PAB given XY. And now, for example, let's say you had a point over here that you'd like to simulate. One way to think about it is that you could say, hey, all right, this point is obtained as a convex combination of this point and this point. But another convex combination might be, well, let's And so what you'd be saying is that, hey, this black point over here, this input probability, this input vector can be simulated or can be written as a combination of either these 2 points or can be written as a combination of these 2 points. Now, it might happen that, you know, well, both of you give exactly P of AB given XY, but let's say these one end up having a smaller communication cost than these 2. And so this would be the better convex combination to use than this one. So we train the algorithm to recognize what are efficient decompositions of the given input vector. So learn to recognize what are the decompositions that minimize the communication cost for simulating the input. And so in some sense, if you could always identify, hey, here's the decomposition that minimizes the communication cost, then as a consequence, we've also figured out the minimal communication cost of this input vector. Right, so one could imagine that the and here I haven't fully thought through the details. So there are how many? So there are 2, 2, 4, 4, 8. So for the 16-dimensional vector, you know, so there can be 4 choices of deterministic vector over here, 4 choices over here, 4 choices over here, 4 choices over here, right? So in total, there are 4 to the 4 possible deterministic strategies. So there are 4 to the 4 deterministic strategies in total for this case. Right, so what are we essentially saying? We are saying, hey, you know, pick any one of these entries to be 1 over here. Pick any one of these entries to be 1 over here. Pick any one of these entries to be 1 over here, and pick any one of these entries to be 1 over here. So that gives us 4 possibilities for each of the individual 4 probability vectors. And so that's your 4 times 4 times 4 times 4. That's your set of possible strategies. So, you know, in the summation that we're doing over here, that's the range of I will go from kind of 1 to 4 to the 4. So there are so many deterministic strategies that we are working through. And then what we have got to figure out, all right, you know, what's the probability weightage Q sub I that I should associate with the D such that the resulting some strategy that I get, the resulting vector that I get is close enough to P of AB given XY. So that's the first thing, that I want it to be close enough. And then the second thing will be, well, given that I now get a vector that is close enough to P of AB given XY, what is the communication cost for it? And that would be relatively easy to do because for each deterministic strategy, you can think of this the communication cost as basically either being 0, 1, or 2. 0 in the sense that it's a local strategy and there's no communication required. Both Alice and Bob can do it locally. 1 bit of communication in the sense that only Alice needs to send her bit to Bob or vice versa. And 2 bits if really both of them need to send their input bits. So you just have kind of, so the communication costs will be and this was also discussed in the, I think, the Peronio paper. The communication cost itself will be just sigma Q sub I plus sigma Q sub j times 2. So here, these are maybe only 1-bit communication strategies. And these are the 2-bit communication strategies. Right, so this gives us the expected communication cost. We are just summing over the probabilities of how many strategies are we using that use 2 bits of communication, and then we are multiplying with 2. So probability with which we use a 2-bit communication strategy multiplied by 2, probability with which we use a 1-bit communication strategy multiplied with 1. Add up these 2 things, and you get essentially the total communication cost. Right. So the idea is essentially, in some sense, you've got multiple possible choices for these Q sub i's and Q sub j that may give us a decomposition that's close enough to P of AB given XY. So one thing is we find the QIs and QJ that give us 2 things. One, close enough decomposition of P of AB given XY, and 2, minimize the communication cost. Right. So the idea would be we use the protocol that we already have to first create a sample of test data where we say, all right, given a particular P as input, this is a known optimal decomposition of that strategy. Or this is the optimal communication cost, and that communication cost can be thought of as being decomposed into these specific deterministic strategies. Here, there might be, I'm not sure whether, so the protocol that you guys implemented only outputs the actual communication cost, right? It doesn't really output the strategies in which it breaks down, right?
Just the communication cost, as far as I remember.
Right. Right, so we might have to think about how we modify that to first also allow us to, or actually, no, that's fine. We just say, all right, we know that the optimal communication cost that is achievable is this, and then what are the, right, so the neural network gets trained on saying, hey, for these strategies, this is the optimal communication cost. Now, based on this, train your parameters such that well, if the communication cost is this, what do the QIs and Q sub j look like? And then based on that, figure out now in the do this in the training process, and then in the testing process, we've got to figure out, given a particular P, what's the new communication cost for it. So there are a bunch of kind of leaps of faith here that we really would need to figure out how to work through. But is the bigger picture kind of okay in terms of what I'm suggesting as a problem?
Yes, sir.
Any questions?
Sir, not directly related to this problem, but you were saying earlier that there are many directions in which this project can go. So, if you can give a brief idea about what all other directions there might be.
Well, so I think one of the directions that you guys identify is basically just identifying the open problems that follow from the paper itself, right? That, all right, here's kind of the range of probabilities P for which we don't know what the optimal strategy is, optimal simulation cost. So any kind of approach to figure that one out. Then another approach is to say, all right, here we've got a protocol for 2 parties. How could you generalize this protocol to work for 3 parties? Right. So now, could a similar protocol be constructed for doing a construction of the optimal communication cost for 3 parties? So those 2 are probably the most obvious ones that kind of emerge from the paper themselves. That's so you take exactly the formulation that you had for the protocol for 2 parties and exactly the protocol that you've implemented, but now say, all right, I want to solve this problem for 3 parties rather than 2. So rather than just having measurements for Alice and Bob, let's say you've got Alice, Bob, and Charlie. All of them are getting a bunch of inputs based on which they do a bunch of measurements and get some correlations out. And then you say, all right, what's the communication cost for the corresponding strategy?
Got it, sir.
So,
sir, will it be a wise idea to work on 2 of these problems side by side, or are they totally different directions?
no, I think it totally makes sense to work on multiple directions because we don't know which one actually works out. So maybe even within among yourselves, you kind of break up. I wouldn't say completely compartmentalize it. Everyone should know whatever is happening in other kind of directions. But let's say, so if Yasmin is more familiar with ML, then she kind of thinks more about the ML approach. If you're more familiar with, hey, what's the protocol we implemented and what to do, or I have some ideas about how to generalize it to 3 parties, then you say, all right, let me try to just construct the 3-party variation of this protocol and see what comes out of it. Having said that, I'm reasonably sure that other, for example, the author himself of that paper would be working on a similar problem as well, because that's the most obvious generalization of this result, right? Hey, I've done it for 2 parties, now can I do it for n parties? So it might be also something like where you're working on something, but then 6 months down the line, you realize, oh, someone just posted a paper in archive that solves exactly this problem. That happens in research. That's not a deal breaker. Then you just kind of feel, all right, what is it that they did that we weren't able to do within our time frame? With the ML approach, I'm reasonably confident that, it's like no one is actually working on exactly this. People are thinking about it, but perhaps not exactly this. You could even potentially combine the ML part and this part by basically saying, hey, given that we know how the 2-party protocol works, could we try to learn how a 3-party protocol might work? So all of this really does require us to bring in some, good understanding of ML into the project. And how would you formulate the protocol, learning the protocol itself as a learning problem, right? So you figure out, well, these were the parameters of the protocol. Now, if I were to look at the space of all possible protocols, what does that look like?
Yes, sir.
So I think I'll try. So I don't know whether I want to say anything more technical about this. I'll try to share resources on neural networks and what papers are out there that have looked at doing non-locality machine learning applications, and then see if we can gather something from that in our next meeting.
Okay, thank you.
So, can you tell about when we'll be starting with the project again? I'll be currently unavailable due to some commitments. So
When will be starting?
I
Sorry,
can't really. The restarting of the project work.
okay.
I was a bit. So I would be available only after mid of May.
Only after mid of. I think that's fine because we agree that all 3 of you are interested in to work on it. For now, tentatively, we say till the end of the year, and then whenever but during this time period, whenever someone becomes unavailable, we realize, all right, that person is not working on the protocol, on the project for that period. So I would say, given that we've discussed this, let's say if Yasmin is available, she can start thinking about the ML aspect of the problem right now, and we realize that, all right, you will join the project when you're available, come in.
For the time being, you surely can share the resources on neural networks.
Sure.
And I'll try to read it, but yeah. And
Now,
another
I
thing,
guess, sorry, just one
Yeah.
logistics issue. I'm not sure whether we would still retain access to the channel that we have on the QUAE server. So
can you make a server, a new server, sir, or should
yeah,
one of
sure.
us?
Like if that, yeah. So I'll just set up a new server and then send all of you invites so that we can work there.
Yeah, yes, sir. That works, sir.
All right. You were saying something else as well, I think.
I was just mentioning this, sir.
Oh, okay.
The server issue. Yes, sir.
Anything else to discuss?
No, thank you.
All right. So Yasmin, do you think maybe the neural network approach doesn't seem reasonable? Like, do you think that's something you'll be able to kind of follow up on in terms of what kind of ML approaches might be useful here?
Maybe maximum likelihood estimation,
Okay.
least square estimation, Bayesian approach. I can try.
Sure. Like it would be great if, like, whenever you get a chance, you think about this and see if you can formulate the problem that we have as one of these within one of these frameworks.
Yes.
Awesome. That would be great.
Okay.
And then I guess that's it for today. I'll share the stuff on the new. I'll create the new Discord server and then share the resources with you there. And then we can continue our communication there. All right.
All right. Okay.
Yes, sir.
I will stop
Sounds good.
the
Recording.
recording. Yes, I am.